Hey everyone! Happy winter and happy holiday season from Lotus Scit. To celebrate, as only we can, we've created a Christmas calculus problem featuring everyone's favorite jolly old elf, Santa Claus. In this problem, Santa Claus and his reindeer soar through the sky on Christmas Eve. His position over the Atlantic Ocean, measured in miles east of New Jersey, is given in the following chart as a function of time, with time being in seconds. This derivational calculus problem is geared for high schoolers and those taking AP Calculus. However, anyone who loves calculus or wants to get into the holiday spirit is welcome to solve this problem. I'll leave it up on the screen for a few seconds in case you want to pause it and try the problem yourself, which I recommend. Otherwise, we'll go through the answers right now. What is Santa's average velocity over the Atlantic Ocean between 2 seconds and 5 seconds? To do this problem, we can use our table of values to examine Santa's various positions per time. We remember that average velocity is equal to a change in position over a change in time. This can be rewritten as x2 minus x1 over t2 minus t1, where x2 is our final position and x1 is our initial position. If we take x1 to occur when Santa is 2 seconds away from New Jersey and x2 to occur at 5 seconds away from New Jersey, we can rewrite this equation as 375 miles minus 125 miles over 5 seconds minus 2 seconds. This solves out to become 83.3 miles per second. Part B. If Santa's average position over the Pacific Ocean, measured east of Japan, is represented by the function x of t equals 60t squared plus 40t, where x of t is in miles and t is in seconds, then what is Santa's velocity 3 seconds after leaving Japan? So here we're not talking about the Atlantic Ocean, so we can't use the table from the previous problem. However, we are given an equation for position over the Pacific Ocean, which reads 60t squared plus 40t. Here, we remember the definition of instantaneous velocity to be written as v equals dx over dt, which is calculated as a derivative of the position with respect to time. In this way, Vt is said to be equal to 120t plus 40, where Vt is the velocity in miles per second, and t is still time. We're not done yet though, because we now need to plug in 3 for t to determine Santa's velocity at 3 seconds. We do this and find his velocity to be a staggering 400 miles per second. This may seem large, but remember, it's Santa Claus. Part C. Does Santa ever travel west over the Pacific Ocean in this model? How do you know? How can we find out if Santa travels west given only an equation? So this problem assumes that east is synonymous with positive values for x of t. Therefore, west must align with negative values for position, and a westward moving direction must indicate a negative velocity, since velocity is a change in position. We therefore need to find out when v of t is negative to find out if Santa is traveling west. So we can use a number of techniques to solve this problem, including graphing, algebraic manipulation, but it's probably easiest to approach it conceptually. We know that time can never be negative and is always increasing because even for someone as magical as Santa, there is no negative time. So we plot a number line starting at 0, and we find that as time moves forward, Santa's position is always positive, and his velocity is always increasing, at least to a point. Therefore, his velocity is always positive or eastward direction. That means that Santa is never moving west. Like I said, we can also use a graphical or algebraic model using the first derivative test to determine when Santa would change direction over any time t, positive or negative. But since we're considering time to only be positive, this method works quite well, and we find that Santa is always traveling east and never west. Part D. Say Santa maintains a constant speed over the Pacific Ocean starting at 6 seconds, and that Santa's average velocity over the Atlantic Ocean from t equals 1 to t equals 6 is 1/4 that of his instantaneous or actual velocity at t equals 6 seconds. If these conditions are so, then when is Santa traveling faster? 6 seconds after leaving New Jersey or 6 seconds after leaving Japan? By how many times? Oh wow, this is a loaded question, but we can break it down. So the first clause of this problem tells us that Santa keeps a constant velocity after traveling at 6 seconds. This is mainly because we don't want Santa to be accelerating at crazy speeds and not being able to deliver presents. The second cause of this problem says that Santa's average velocity over the Atlantic Ocean, in other words, what we would calculate from 1 to 6 seconds given his distance, is a quarter of what he is actually traveling at 6 seconds. Remember that instantaneous velocity and average velocity don't always mean the same thing. And in this case, we know that Santa is traveling 4 times faster at 6 seconds than the average velocity. Therefore, we get an equation, VA of 6, or his velocity at 6 seconds, is 4 times the average velocity that we would calculate. So to actually solve this problem and determine which one's faster, we need to calculate Santa's actual velocity at 6 seconds when over the Atlantic Ocean. Well, his average velocity is 90 miles per second, and we get this using the values in the table. So his actual velocity is 4 times that, which is 360 miles per second. That is his speed after leaving New Jersey. Now, if we look at the Pacific Ocean after leaving Japan, we can plug 6 into our equation and find that he is traveling 760 miles per second after leaving Japan. Santa is traveling much faster over the Pacific Ocean than he is at the Atlantic Ocean, which means he is traveling faster 6 seconds after leaving Japan than after leaving New Jersey. To find how much times faster this is, we simply use a proportion. 760, or VP, over VA, which is 360, is equal to 2.1 times. So therefore, Santa is traveling over twice as fast over the Pacific Ocean as he is over the Atlantic Ocean. But don't worry, he'll still deliver the gifts and eat all of his cookies on time. I hope you enjoyed that problem, but even more importantly, I hope you have a wonderful holiday season and a happy new year. It's certainly been a skitty 2020, but here we're all hoping for a much brighter 2021. So from all of us here at Dippy Studios, have a happy holiday season and a very Merry New Year.